with quaternions. Parameterization of hypercomplex multiplications with 1 over n parameters. As we know, fully connected layers, also known as FC layers, are pervasive. Such layers transform an input vector of dimension d into another output vector of dimension k. As the name suggests, FC layers are fully connected, and the parameterization cost of such layers are dominated by the weight matrix, which is a d by k matrix. That's why the parameterization cost is on the order of the product of k and d. So in practice, when the input size or the output size are big, then the parameterization cost can be very high for the FC layers. That's why recent works propose the fully connected layers with quaternions to reduce the parameterization cost. So for context, a quaternion is a 4-dimensional hypercomplex number, and the multiplication of 2 quaternions is called the Hamilton product. And the so-called FC layers with quaternions just replace the real-valued matrix multiplications in the FC layers with the Hamilton products of quaternions. So note that the FC layers with quaternions has only 1 over 4 parameters in comparison with their FC layer counterpart. So as you can see in the matrix form on the left, this quaternion trick can reuse the parameters 4 times via the Hamilton products. So that's why you can, as we just mentioned, such trick will enable the FC layers to have only 1 over 4 learnable parameters. However, beware that the hypercomplex multiplication rules only exist at very few predefined dimensions, such as 4D, 8D, and 16D. So in view of this, we propose to learn the multiplication rules from data, regardless of whether such rules are defined on arbitrary dimension. So by doing this, we can provide more architectural flexibility using the arbitrarily 1 over n learnable parameters compared with the FC layer counterpart. So how we do this? So look at this. So compare with our previously shown FC layers. So here we just replace the matrix W with the matrix H here. And the matrix H here is still of the same size, which is a D by K matrix. However, we construct the matrix H by using a sum of n Kronecker products. And Kronecker products will reuse the parameters. And by using n independent Kronecker products, we can reuse the parameters n times, which will allow us to have only 1 over n learnable parameters in such layer. And since here is a parameterized hypercomplex multiplication, we call this layer PHM layer. And as illustrated on the right-hand side, you can see that although the constructed matrix H can be of a bigger size, the actual learnable parameter size of such a matrix H can be much smaller than the size of H. So mathematically, the parameterization cost of the PHM layer is on the order of KD over N. So here you can see that our parameterized hypercomplex multiplication layer has only 1 over n parameters in comparison with their FC layer counterpart. So here, note that the hyperparameter n is specified by user. So means that if you use more Kronecker products in the sum, you end up with more parameter saving by replacing the FC layer with the PHM layers. So mathematically, the PHM layers can subsume the hypercomplex multiplications and the real-valued matrix multiplication. So this can be seen as a breach of the existing multiplication rule between the real space and the hypercomplex space. And empirically, on artificial dataset, we also show that the PHM layers can indeed learn to perform the existing multiplication rules, such as learning the rotations in 3D real space and the Hamilton products in the Quaternion space. To demonstrate the effectiveness of the PHM layers, we try to equip the existing LSTM model and the transform model by replacing the FC layers or the matrix multiplications with the PHM layers, while keeping the rest unchanged. So we end up with the PHM LSTM and PHM transformer models. Okay, so here are the experiments. So first, on the natural language inference tasks, we can see that the PHM layers can reduce the parameters and improve the performance with the flexible choices of the hyperparameter n. So as highlighted in the green boxes, you can see that when we increase the hyperparameter n, we can enjoy more parameter saving as expected, while the performance can actually partially match the other baseline or even improve the baseline. So which is pretty encouraging for the LSTM models. Then for the transform model, we first evaluate on the neural machine translation tasks. So first of all, we can observe like the similar results, like when we increase the hyperparameter n, we can enjoy even more parameter saving, and at the same time, we can even further improve the performance with such flexible choices of the hyperparameter n. What is more, on the bottom 3 rows, we also double the hidden size. So we call this rescaling with a factor of 2. And in this way, after we double the hidden size, and then we try to reduce the parameters by replacing the fully connected layers or the matrix multiplication with the PHM layers, we can also obtain even more effective representations, which will allow us to further improve the performance. So you can see that this is pretty powerful for transformer, because in transformer model, we have a lot of the matrix multiplication, such as on the multi-head attention and the position-wise feed-forward networks. So we can just replace all these matrix multiplication with the PHM layers to enjoy the parameter saving while achieving the comparable performance. And in practice, the PHM layers do not increase much computation costs. So for instance, when we choose n to be 8, the inference time is reduced a lot because we reduce the number of parameters to a bigger extent. And the training time is also pretty comparable with that of the standard transform model. And similarly, we can observe the similar results, like reducing the parameter while improving performance on more NLP tasks like text style transfer and the subject-verb agreement tasks. So in summary, in this work, we proposed the parameterized hypercomplex multiplication layers, which is the PHM layers. These layers can learn the multiplication rules from data using arbitrarily 1/n learnable parameters in comparison with the fully connected layers counterpart. And in the experiments, we also show that these PHM layers can improve both the LSTMs and the transformers on multiple NLP tasks, such as natural language inference, neural machine translation, text style transfer, and the subject-verb agreement tasks. Thanks.
So moving on to the last paper on quaternions, there was a question from the audience. There would be many possibilities of reusing parameters. What is the reason why you choose quaternions? And to that, I can add, so have you considered other sort of low-rank factorization methods or tensor train and various other low dimensional representations of full connectivity matrix?
So yeah, so first of all, in our early experiments, we did try some low rank, like the low rank approximation, which is like a very commonly used parameter saving or compression techniques. It will degrade the performance a lot. Then we just follow the recent Quaternion neural networks model, and then we try that, and empirically we find that these models work very well on a few of the NLP tasks that we have investigated. Then we move on to see how we can generalize such Quaternion-based compression techniques and see how we can even learn those Quaternion multiplication rules by parameterizing these rules using our own method. So then we just propose our method and we compare with those Quaternion-based method. And we also find that since our PHM layers can outperform or even perform comparatively with those Quaternion-based model, and those Quaternion-based model can outperform those low rank approximation. So it means that our model is still more effective than like the low rank approximation. But I think that there can be even other compression techniques that we can also see how we can generalize their operations, which could be a very promising future directions.
Okay, great. One final question is, do you think this is more amenable to quantization of parameters?
So yeah, so quantization is also quite a popular technique for reducing the models. And I think so first of all, in our work, we show that we can really recover those multiplication rule in the hypercomplex multiplications, which can be represented by like the small digits, like integer, like -1, 0, and 1 in a matrix form. And since we can recover that, and we can learn this by using the FP16 or FP32 representations, then in this way, we can just recover the integers by just rounding them up to the nearest integer numbers. So although in our work, we haven't investigated like how we can just further improve the compression efficiency by just outputting the integers rather than the floating numbers. So this could also be a future work.
Okay, great. Let's conclude with one question from the audience. From your results, it seems the bigger value of n results in more parameter savings and even better performance. And they ask if you've considered, but the largest value you used is as n equals 16. Have you experimented with larger values for n, and what are the results?
We haven't tried beyond 16, but we do 16 because 16 is also an existing dimension for the in the hypercompact space. But we do try some other dimensions like 10, 5, which are actually undefined mathematically. Mm-hmm. So, but when we experiment with 16, in most of the experiment, actually the accuracy drop a lot. So like this is a natural trade-off between the parameter saving and the accuracy.
So the optimum is the under 16.
Yeah, we try all the experiments at 16 or under 16. Nothing beyond 16. Because the 16, when we see the accuracy drops, then we don't go beyond 16.